Alright, in section 4.5 we're going to look at exponential modeling, and the general equation looks like this: A equals A0 times e to the kt, where A is the future amount, A0 is the initial amount. So we start, for example, this first problem is on population. So we have an initial population, and then it's going to grow over time. So we have a future amount. So this is the initial amount. E is the natural number that we've been studying, so it's a base. And it's approximately equal to 2.718. But don't use that number, use the actual button on your calculator. There should be a button on your calculator that says E on it. K is the growth rate if K is bigger than 0, and it's the decay rate if K is less than 0. So our population might be growing or it might be shrinking over time, and decay will determine if it's growing or shrinking depending on if it's positive or negative. Finally, T is the time. And it could be years, it could be days, it could be minutes, any unit that has time involved. And whatever the unit is, that's what you will report. So in most of these problems, we're going to deal with years. So then if I do any calculation, it has to be based on years. Okay, so let's look at this first problem. The exponential model A equals 419.7 e to the 0.032. So let's start identifying. A0 is the 419.7. The K is 0.032. And it says that model describes the population A of a country in millions T years after 2003. Use the model to determine the population of the country in 2003. So this one's a little bit interesting right out the gate, because year T is measured as years after 2003. Then they measure the country in 2003. So this is the unique case where time is 0. So there is no, we haven't passed a year yet, so let's see what the model will do. So the future amount is going to be the starting amount, 419.7 e to the 0.032 times time, but time is 0. So this is going to give us 419.7 e to the 0, but any number to the 0 is just 1. So this is 419.7 times 1, which is just 419.7. So this is the unique case where, in essence, all they're really asking for is the initial amount, which we could have just said, oh, it's 419.7. So if time is 0, your amount is your starting amount. Okay? But you can see it with the math there. By plugging in 0, you get it to simplify to that number. Okay, that's the first one. Okay, in problem 50, they just want us to identify which country has the greatest growth rate. So if we look at these, the growth rates are these numbers. Now, these are decimal numbers, and we want to write them as percentages to compare their rates as a percentage. So to do that, you just have to jump each of these decimals 2 to the right. So to convert a decimal to a percentage, just jump the decimal 2 to the right, and we'll add a percent sign. So this first one would be 2.5%. This next one would be 0.1%, because the decimal is before that 1 there. But notice country 2, that's decay. So this minus sign means that this country is actually decaying or getting smaller. The population is shrinking. This next one is 1.3%. And this last one is 0.5%. So just looking at the biggest number, it's clearly country 1 with this 2.5%. So country 1 has the greatest growth rate, and the percentage growth rate for them is 2.5% each year. so hopefully not too bad there, just converting from decimal to percentage. Okay, in 51, they want us to look at which country is decreasing the most. So which country has a decreasing population? A decreasing population means that the k value should be smaller than 0 or negative. So we just quickly look and we see the only two negative decay rates are right here, countries D and E. So countries D and E are decreasing population. Now it just wants us to convert this to percentages. So this is going to be, jump our decimal again, 1, 2, 1, 2, and we're going to have, let's see down here, 0.4% for country D, and 0.3% for country E. So we would record 0.4% for country D and 0.3% for country E. Okay, so just identifying which ones are negative and then converting to a percentage. Okay, 52. The exponential model A equals 983.1 e to the 0.019t describes the population A of a country in millions t years after 2003. Use the model to determine when the population of the country will be 1259. So in this one, they have told us the future amount. They said the future amount A is 1259. The starting amount is 983.1. Growth rate, because it's positive, of 1.9%. And they want us to solve for t. So we're going to actually derive an equation here. We're going to start with the original equation, and we're going to rearrange this to solve for t. So we want to have t on the left equal to some new equation. And we need to just use one property of logarithms, and that was this one. If you have the logarithm of x raised to some power, that is the same thing as the power times the logarithm of x. So we had seen this maybe a lesson or two ago. The powers will come down front. So that's how we're going to unbury t. So we've got to get t to not be a power anymore. And the way to do it is to take a logarithm of both sides. But before we take a logarithm, we're first going to divide both sides by a0. So I can't have this a0 over there, so let's move it over here. And so we're going to get a over a0 equals e to the kt. And actually, there's an even simpler form of this equation. Let's write that. Actually, no, let's keep going this way. Okay, so we have a over a0. Now we're going to take a natural log of both sides. So we're going to take the natural log of a over a0. If I take a natural log of the left, I have to take a natural log of the right, e to the kt. Okay, now we're going to use this property in blue. So we are going to be able to pull this entire exponent, which is both of these things, down in front. So we are going to have natural log on the left, a over a0, equals kt e, natural log of e. Natural log of e. So the kt is now in front. And there's a property we also studied that said this. If you have the natural log of e, natural log is really base e. So it's that pattern of log, base, and then if the number is the same as the base, this equals the power of e, which is in this case is 1, so it's equal to 1. So this whole natural log e will just go to 1, and 1 times kt is just still kt. So to solve for t, the last step is to divide both sides by k. So let's divide away this k, divide it over here. And so we can write t is equal to the natural log of the ratio of a to a0, all divided by the growth rate or decay rate, depending on what it is. And now we have a new equation. And now this equation we can use and just plug and chug into using our numbers to get whatever we might be interested in. So let's plug in the numbers we have. So the time for this population to grow to that number is going to be the natural log of A, which is 1259, divided by the starting amount, which was 983.1, all divided by the K, which is, leave it in decimal, 0.019. Now the trickiest part about this is getting this right in your calculator, and then rounding properly. If you do the top, you should get this number, or at least close to it, depending on how much you round. 0.24736. And we discovered in my class, face-to-face class, that if you don't round, if you don't keep as many digits as me, you're going to get slightly different answers. But they should be close enough where we say, okay, that's just rounding. It's not that you've done something wrong. You just might not have written down enough digits. Okay, now if you divide those two numbers, you should get 13.02. And so this means it's been in 13 years. So if they're talking about years here, our units are years, so this time will be years. Now the last little hiccup for this one is they want the calendar year. So if our population starts in 2003, and we're predicting 13 years later is when we're going to have this population reaching 1259, the final answer is going to be 2003 plus 13, which would be 2016. And that's going to be the final answer. So if our population is growing at about 1.9%, we start at 983 million. In about 13 years, 2016 will have 1,259 million people in the country. So that's how we would do that. In 53, they want us to do a slightly different equation. So what they want us to do is to solve for k. Well, we're going to use that same formula we just had. So time is the natural log of the ratio of the amount you have to the initial amount you had divided by k. Well, we can actually multiply both sides by k and then divide both sides by t. In essence, we can swap t and k. So you can come in here and say, let's swap this term for this term. The way they're separated by that equal sign, and one being a fraction, you can do this sort of swap. So we can get a second equation that says k is equal to the natural log of the ratio of the amount you have in the future to the starting amount divided by time. And that's the equation we're going to need for this problem. So for this problem, they say you start at 30.3 million, your future amount's 45.3 million people, and the time, t, is the difference in 2042 and 2007, which is 35 years. So plugging all this in, your decay or growth rate, depending on, well, it must be growth rate because the population increased, so we're expecting a positive k out of this. We would have 45.3 divided by 30.3 divided by the 35 years, and you'll get, on top you should get a number close to this, 0.402159, and then 35 on the bottom, and you should get 0.0115, something like that. And to 4 decimals, that would be the answer, 0.0115. So their growth rate's about 1.1%, just a little bit above 1%. Now do 53. Okay, in 54, it's a straight up plug and chug the original equation. So it says we have an artifact originally had 16 grams, carbon-14 present. The decay model is 16 grams, that's the starting amount. E to the minus, so notice this is decaying now. You're losing particles. So this is called radioactive decay. Describes the amount of carbon-14 present after t years. Use the model to determine how many grams will be present in 7,066 years. So they told us t. So we just have to plug all this in. 16 times e raised to the negative 0.30121 times the time, which is 7,066. And then the only hard part on this is getting it right in your calculator. So if you take that really small negative number times that 7,000, you should get the power on E is now negative 0.854986. Then if you take that exponent button, so E button on your calculator, so that power, so again, find that button on your calculator, you should get that whole thing becomes 0.425289. Then the last step is to take that number times 16, and you should get 6.8. And they want us to round to the nearest whole number. So to round to the nearest whole number, we stand at the whole number, look to the right, it's 5 or bigger, so we're going to plus that by 1, and we'll call this number 7. So in 7,000 years, you're going to have 7 grams of your carbon-14 when you had 16 to start with. Now that's an interesting number. Half of 16 grams would be 8. We have 7, so we have less than half, which is going to bring us to our next topic of a half-life. So how long until you have half of your starting material? So let's look at that. Okay, so in 55 it says the half-life of the radioactive element, unobtainium-43, so they have a made-up element here, and they say it's 5 seconds. So that's the half-life, 5 seconds. Half-life means I have 50% of A0. So the amount you have now, A, is 50% of your original amount, half. So this problem is not too bad. If I start with 80 grams, after 5 seconds I will have half of 80, which is 40. So that's 1/2 of 80. After 10 seconds, so as long as these numbers increment by 5, which is the half-life time, then I'm going to get half of the previous result. So this number is going to be half of 40. So I'll get 20 grams left. Then this incremented by 5 again, so from 10 to 15, so half of 20 is 10. Then it increments by 5 seconds again, so I use half of 10, which is 5 grams. Incremented by 5 again, half of 5, 2.5 grams. So this is kind of a quick and easy illustration of a half-life in that half-life time. So every 5 seconds, as long as it increments by that, you just have your numbers. So 40, 20, 10, 5, down to 2.5. Shouldn't be too bad. We can do that in our head. Okay, so 56 is going to say, not a half-life per se, but it says, how long will it take until we have 12% of the original carbon left? So to solve this, we're going to rearrange our equation ever so slightly. So we're going to notice that if you take A, the amount in the future, divided by A0, your starting amount, if you divide those two numbers, that is the percentage of what you have left, of what is left. So if things are decaying, just dividing those two numbers in that order, which is what the equation is doing, that is telling you the percentage of what you have left as a decimal. So we can rearrange our equation. We said T was equal to the natural log of A over A0 all over K. Well, we can rewrite this now. Instead of A over A0, we can write the time as the natural log of the percentage left as decimal all over K. So if they tell us they have 12% of the original carbon in this painting that they found in this cave in France, we're going to use 0.12. So to change to a percentage, for percentage to decimal, just take your number and divide by 100%, which is also the same as jumping your decimal to the left. So we can just take that 12%, the decimal's right there, jump it to the left, and get 0.12. Okay, so that is how we convert to the decimal we need. And so we just plug this in. So the time it's going to take to go from 100% to 12% is the natural log of 0.12 divided by k. K in this problem is this number, negative 0.000121. And if you do this, you should get, on top, negative 2.12026. On the bottom, this small number, 000121. And then you divide those two numbers, you should get 17,522.84. And they want us to round to the nearest integer. Integer means whole number. So stand on the 2, look at the 8, it's 5 or bigger, plus this by 1. So the final answer is going to be 17,523 years. So basically we're saying this painting is 17,000 years old. So very old painting, and this is a powerful technique to do things like carbon dating and find out how old things are. Because we know very accurately how these elements decay. So that's something we can measure in a lab very, very accurately, and it's constant, and it remains the same throughout time. So once we know carbon-14 decays at that percentage, then we can estimate how much it should have been there to begin with, and we can measure how much we have left. We can figure out how old stuff is. K57 is going to be very similar. They say we have the half-life of a certain radioactive substance, and so we know the time, the half-life time. And they want us to solve for K. So K is going to be really similar. It's going to be the natural log of the percent left as decimal, divided by time. Well, if it says half-life, that means that we have 50% of what we started with. We have 50% left, which we're going to change to 0.50. So we just have to plug in 0.50 here, and then divide by the time it took, 2,503 years, and we'll get, if you do this correctly, negative 0.3012327,693. That's a lot of decimals because it wants us to round to 6. So we're going to count. 1, 2, 3, 4, 5, 6. Stand there. Look to the right. It's 5 or bigger, so we're going to plus that by 1. And we're going to record the K is negative, don't forget that, 0.123277. Okay, now, because we're working with such small numbers, your calculator is likely to write this as, so your calculator is likely to write this as negative 2.7693, and then it's going to write e to the negative 4, or it might show it like this, negative 2.7693 times 10 to the minus 4. These are all saying the same thing, so your calculator is writing this in scientific notation. And that is to show more digits. So if it showed you all those zeros in that small screen, it's not going to be able to show you a lot of the digits. So it's going to switch it to scientific notation. Now, how do you handle that? Well, the way you handle it is, if you're starting with negative 2.7693, this negative 4 power is telling you how many jumps to make with your decimal place. And if it's negative, it's jumps to the left. Make the number smaller. So I'm going to jump this 4 to the left. 1, 2, 3, 4. And in place of these open spots, we're going to write zeros. So 1, 2, 3. The decimal's now there, and then we add a leading 0. And then we have to also put the minus sign back over here. So we have the same number, but just be careful. Your calculator is probably going to show it to you differently, and you're going to have to physically on paper do those jumps so you can get the right rounding and get the same number that I have shown here. 58 is pretty much the exact same type of problem. We have a half-life, so we're using 50% or 0.50. And our time now is 16.3 days for this radioactive substance. So we're going to take the natural log of 0.50 and just divide by this 16.3 now. And if you do this one, you should get negative 0.0425243. And to 6, one, two, three, four, five, 6, stand there, look at the right, it's not 5 or bigger, so you're just going to stay at the 4, stay with the 4, so we would record the decay rate for this substance is 0.042524. Okay, the last two are very similar. They're going to use the same steps. So in the first part, they're going to give us the half-life, so the 50% left marker. And it says the half-life requires 22 years. So we're going to just use that information to solve for K, like we did in the previous problems. So step 1 is to solve for K using the natural log of the 50% amount, and then you have to use the amount of years for the 50% amount, which is 22. So you're going to divide those two first, and for this one you should get negative, decaying, 0.0315. Then in step 2, try to use color here to help us here, you're going to use that K to solve for an unknown T. So we're going to have T is equal to, so now we have this constant decay rate, and it's going to say, okay, I don't know how many years, but it gives us a different percentage left. So now the percentage left is 81. So we're going to use that in the equation. So it's going to be the natural log of 0.81. And now we're dividing by the same K we had before, that we just solved for. So this is going to go down here. And if you do this, you can solve for the time to be 6.69. They want us to round to 1 decimal. So we'll stand on the 6. It's bigger than 5, so we'll bump that up by 1. So we'll say 6.7. And whatever units they gave you, years here, is going to be the units for this answer. So in 22 years, I have 50% of my substance, which means if I want 81% of the substance, it's going to be fewer than 22 years. So closer to 7 years. If I wanted less than 50%, let's say they said 20% of your substance, well, that time's going to be longer than 22 years. So every 22 years, I'll have half of my original substance. Okay, the last problem is the exact same approach. This is the amount of tranquilizer in the bloodstream. So that's another application of these kind of models, is when you take a painkiller or something, the main ingredient, the chemical, spikes in your bloodstream, but then over time it's going to go out. It's going to be cleansed by your body and removed. And so this is why you have to, like painkillers like Tylenol and Advil, they say on the bottle, take, one every 4 to 6 hours. So you take one, it spikes in your bloodstream, and then it's going to decay, and then 4 to 6 hours later you take it again, it spikes, not as high as the first time, it'll spike, and then decay, and you get this kind of sawtooth pattern of spiking it and then decaying. Okay, but it's the same approach. We're going to have a half-life number, so that's our 50%, and for this one it's 43 hours. So step 1, find the decay rate if you have 50% after 43 hours, and this one's going to be negative 0.01612. Then step 2 says, now find time for the new amount left, 0.94. So it's going to be the natural log of 0.94 divided by this decay rate we just found. And the time for this then will be 3.84. Now, if they used hours, we're going to call this hours. And to one decimal, we will say that this is 3.8 hours. So in 43 hours, you'll have half the tranquilizer in your system, and to have 94% of the tranquilizer in your system, that will occur after 3.8 hours. So pretty powerful drug to stay in your system that potent that long. Okay, that will complete 4.5 and complete chapter 4 for us.